As I told you before, seismic analysis or lateral load analysis for building, it's really a huge topic. And to do this, you have to have a course. Maybe some of you are enrolled in engineering, what do you call it, like structural dynamics for building. So structural dynamics, you study the single degree of freedom, the multi-degree of freedom, you know how to do dynamics analysis for building. All what we did is a static analysis in the first of the semester. We see how static load, like concentrated load, bending moments, all these is static load. But how dynamics load impact the building or the dynamics performance of the building. So these structures are designed to stay still, not to move. But sometimes they have to move when there's wind or something. So how this response look like, you have to study this course. Seismic design is a completely different course. How to do seismic design for buildings. How to quantify the load based on the codes. Load modeling of the building, that's something that you study alone. Like you take the dynamics, you don't like know how much how's the codes deal with the design for wind or design for seismic. So yeah, and definitely seismic and completely different from wind. So you have, maybe you have to have four courses or something to get full perspective on the lateral load design for buildings. Okay, so what I'm gonna do right now in the next 15 minutes, I'm gonna do a little bit of introduction, how we are gonna handle this. I'm gonna give you just the things that allows you to survive the project, like do the things that I need in the project. Not everything, I will simplify things for you. Maybe when you study a course or something, it is not gonna be the same that I did it, but I give it to you in this most simplified way, okay? All right, so let's start this with, like, when we do gravity load analysis, like you have a beam or something like this, or a frame, and this frame has any loads, like distributed load. Oh my god, these move, it doesn't look like me. Okay, so when you have a structure like this, or you want to design a structure like this, first you have to do structure analysis for this structure, right? And once you do structure analysis, you design. That's the A-B steps of a structural design of a building. First, you build the system. Choose the system, flat slab, solid slab, whatever the system is. I build the system, I put the loads, I do analysis to the system, and then once I do analysis to the system, I get two things. First, internal forces. Second is deformations. That's what we do in our design as a structural engineer. We only looking for internal forces, deformation, and then in other courses you will learn design. What does it mean design? Get cross sections and reinforcement if it's gonna be okay? So that's what we do exactly as a structural engineer. We get internal forces, first we build the system, internal forces, deformations, and then design, get what cross section that I should use, either wood, concrete, steel, whatever. You need to describe me how this cross section look like, how much is steel in it, okay? So that's what we do as a structural engineer. Same thing if it's lateral load. So that's number one. Number two, lateral load. Lateral load is a little bit different. Like you have a building like this, and then this building is gonna be hit with a wind, and this wind is gonna make a lateral load in the building like this, which is not what we used to. We used to have all the loads coming down, gravity, live load, dead load, flowing, everything. Or you have a seismic load. The seismic load is shaking the ground, and shaking the ground with non-constant acceleration. Acceleration that it changes every second. Like let's say on the x-axis is t, and in the y-axis is the ground acceleration, ag, and the ag is something like small, and then it hits a peak, and then it dies, and it's something like this. And it takes it that way and that way, so you have positive, negative. So this is how the earth is shaking, okay? So what we are interested in, we are interested when this building is hit with an earthquake, how much bending moment in these columns is gonna have. So when we take a gravity load, the column is gonna have axial force, but when it's hit with a lateral load, the column is gonna bend and it's gonna have a shear. So I wanna find out what is the shear and bending moment on each one of these columns. And I wanna know how much deformation is this building is. Maybe you designed this building to resist the earthquake, but if I live in a tall building in a 60-story and the building is moving and it makes like 1 meter displacement at the top coming back and forth, the building is not falling, but I'm in the 60th story, the water in my cup is like keep moving that way. So it's not comfortable at all to live in this building, okay? So that's what we call the serviceability. We need to make the building like comfortable to live in, okay? So it's same thing, internal forces and deformation, but it's a little bit different from here. Like internal forces here, we're looking at bending moments and shear forces in the columns and everything. Here we'll look at bending moments in the beams and the slabs. Deformation, it's the same thing here, but the deformation is not like deflection, like what we used to. It's here like more like drift, maximum drift the building do. The inter-story drift between the buildings, like how much this delta 2 minus delta 1, that's what we are looking at, okay? All right, usually the tall buildings have earthquake, there's a limitation on the inter-story drift. Delta, like tells you the inter-story drift should be not to exceed a specific value. For wind, there is a limitation on delta, like tells you that H over 500 doesn't exceed, should be less than H over 500. H is the height of the building. Like if you have a 500 meter height, so 500 over 500, it's like 1 meter, which is really huge, but this is what the winds allow, okay? All right, so we have all of these. So to do this, I need to teach you something. The thing is, to do lateral analysis for a multi-story building, it's a really, really huge problem, a mathematical problem that is huge, because you have multi-degree of freedoms. Like every single point here can move separately in X, Y, and Z and rotate X, Y, and Z. It's really a huge problem. So structural engineers start to looking at ways that can simplify this building to a simple model so that we can solve a simple dynamic problem. But to simplify this, we need to come up with a way that we can lump the building into a simplified model. But before I do this, let me do something with you. Let's say that we have this system, and I have this system, and I'm bowling here with force B, and here I have also force B. What is this system? It's a system of bars. Like we always represent bars with the springs. Why? Because if you have a bar, this bar has an axial stiffness, and this axial stiffness we represented with a spring like this. And let's say that this spring has K1, K2, K3, and here's K1, K2, K3, okay? Bars connected like this. All these bars are connected in parallel, and you are trying to pull that way. And this has a stiffness K1, K2, K3, all right? So what is gonna happen here? And here's a very, very stiff body. So that means this body needs to move with a specific delta, like it can't rotate this way or can't rotate this way. So when you pull with speed, all this body is gonna move delta like this, right? So all these springs are gonna have the same delta. Like this spring is gonna come here, and this spring is gonna come here, and this spring is gonna come here. So what is gonna happen is this spring is gonna have a different force. Like this spring is gonna have B1, and this spring is gonna have B2, and this spring is gonna have B3, okay? So that's what's gonna happen. Everyone is gonna have a contribution of this force based on this stiffness. Like let's say that this stiffness is like 10 times of these two. This one is take most of the force. Like you have to overcome this so these two can move, all right? Okay, for this one, all these springs are gonna feel with the same force. All of them are having the same B. Like let's say I have this fixed and I'm trying to pull. All of them are gonna feel the same force. How? Like let's do simple structure analysis. Like if you try to find the normal force here, you either cut and look left or look right, right? So if you cut and look right, it's gonna be B. Here, it's gonna be B. And cut here, it's gonna be also B. So all of these springs are having the same force, but everyone has different delta. Like this one, for example, what's gonna happen? This one is gonna move with, can't see this. Okay. It's gonna move delta 1, and this one is gonna move delta 2, and this one is gonna move delta 3, and this point is gonna move the total delta of all of them. Okay? So in this system, delta is equal to delta 1 plus delta 2 plus delta 3, right? But here in this system, B is equal to B1 plus B2 plus B3. And delta for all of them are constant. Like this one has the same delta, this one has the same delta. All right, this one here is B is constant. So, if you guys remember, do you guys know the Hooke's law? What is Hooke's law? B equal K multiplied by delta, right? So let's substitute this here. So here, you will find that the total stiffness of this system multiplied by delta of this system is gonna be equal to K1 multiplied by delta 1 plus K2 multiplied by delta 2 plus K3 multiplied by delta 3, right? But we know from this system that delta is equal to delta 1 is equal to delta 2 is equal to delta 3. All of them have the same delta. Like all this system came here at once. So you can divide by delta, you will end up that the stiffness of the entire system is K1 plus K2 plus K3, or the sum of all the K's in the system. So if you have a parallel system of stiffnesses, you can basically make a sum of all the K. Like if this is 10, 10, 10, the sum of all the stiffness is 30. That's direct. Let's see here what happens. Same thing. If you have that B is equal to K multiplied by delta, that means that delta is equal to B over K, right? Let's do the same thing here. So B over K is going to be equal to B1 over K1 plus P2 over K2 plus P3 over K3, right? And we know here that all the B is the same, right? So I can divide B, so all this means that 1 over K is going to be equal 1 over K1 plus 1 over K2 plus 1 over K3. So that means that K is going to be equal to, or 1 over K, K1 was K, sorry. Well, we can keep it like this. Don't have to multiply. So, can you see the difference? So that's if the system is in series, parallel, and this is in series. We can apply the same concept for buildings. Look at this building. If you have a building like this, all right, this building, when it gets a lateral force, what is going to happen? It's going to deform that way, right? I want you to look at all these columns. This column is going to move delta, 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 and all of them are moving with the same delta. Why? Because they are attached with the same slab, like this. And the slab, we either go all together or we are going to all stay together. So all the columns here are in parallel. Why? Because they are all moving with the same delta, right? So what I can do here, I can take the sum of all the stiffness of this column, sum of the K, right? To get this, the stiffness of the entire story. So, and I do the same thing for this story, because this story also have the same delta. And this story. So I can convert this building to one big column, and this column has a lumped mass of the slab at each story. Like this. And then this one is gonna be sum of k of story 1, sum of k of story 2, sum of k of story 3, until sum of k of story n. Why? Because I have all the stories are in parallel, all the columns in the same story are in parallel stiffness, so I can sum them as a parallel stiffness. But look at this building. Like right now I did the first simplification. I converted that entire 3D building to one column, and the mass is distributed. Like this is mass of slab M1, M2, until Mn. Then what I can do, look at this. Here is delta 1. And the thing is, this one is taking delta 2. And this is delta 3. So what happens here is the same thing like happened here. Delta 1. And then here is delta 2, which is delta 1 plus delta, the new delta here. And all of them, they are making the final delta of the structure. So the columns from the different stories are in series, right? So actually, I can also convert this to only one big mass of the structure and only one column by taking the parallel sum of the stiffness. This rule. 1 over k is going to be equal 1 over k for story number 1, 1 over k for story number 2. So what did I do? I converted this entire structure from a 3D model to, this is what we call it, multi-degree of freedom system. That was 3D multi-degree of freedom. And here I converted to a single degree of freedom system. That's actually what I did. That's the simplification what we did. Right now, this is a very, very simple structure that we can handle, that we can solve, that we can make an equation for, and it's gonna be very, very easy to solve. I'm gonna show you next time how we can solve it. What I mean by solve it, find the final delta, how much delta this structure is gonna have. But this is exactly what we want to do this simplification. But you will tell me, is that accurate? Yeah, it's with the accuracy that we can accept at that level. But if we were able to do this, that's gonna be much better. And if we're able to do this, this is gonna be much better. Even the analysis software, they do this. They do the multi-degree freedom. But as humans solving things manually, we only can do this. In classes like dynamics, maybe you will solve 2 degree of freedom or 3 degree of freedom. Other than that, it's gonna be difficult, okay? All right, next time we're gonna continue on this and see how we are gonna use this information to do dynamic analysis.